a first step is to write out the sample space. Now obviously if we flip the coin 20 times, this would be a very unwieldy sample space, and you would have to use some counting techniques to calculate these probabilities. But because we've only flipped the coin 4 times, there are only 16 possible outcomes, so it's relatively easy to write out every possible outcome in this equally likely sample space. Well, a first step to finding these probability distributions is to list the possible values for each variable on the left-hand side of your table. So we see x can take the values 0, 1, 2, 3, and 4. Y could take the same values, but z can only take the values 1, 2, 3, and 4. How do I find the probabilities for, let's say, the values of x? How do I find the probability that x equals 0? Well, x, remember, is the number of heads in the sequence. So I look for all possible sequences where the number of heads is 0. Well, that's pretty easy to find. There's only one sequence in the set of outcomes where the number of heads is 0, and that's where we have all tails. So there's one outcome in the sample space which corresponds to x equals 0, and therefore the probability x equals 0 is the probability that that one outcome happens, which is 1 over 16. It's an equally likely sample space. For the probability x equals 1, I have to find all of the outcomes where the number of heads is exactly 1. We see there are 4 such outcomes. In fact, they correspond to the number of places that the head can appear. There are only 4 places the head can appear. And because they're all equally likely, with a probability of 1 over 16, we have the probability x equals 1 is 4 over 16. Well, let's look at a couple of examples from y. Y is the longest run of heads. So to calculate the probability y equals 1, I have to figure out which of the outcomes in the sample space have the longest run of heads equal to 1. Well, I've gone through all of them, and I've underlined the ones where the longest run of heads equals 1. I found 7 in all, and they're all equally likely with a probability of 1 over 16, so the probability y equals 1 is 7 over 16. The probability y equals 2, well, to calculate this, I have to find all outcomes in the sample space where the longest run of heads has length 2. Again, I've underlined them. There are 5 in all, so the probability y equals 2 is 5 over 16. What about the number of runs? What if I wanted to calculate the probability z equals 2, that the number of runs is 2? Again, I go find all of the outcomes where the number of runs is 2. There are 6 in all. You see that they're underlined, and therefore the probability z equals 2 is 6 out of 16. The probability z equals 3 is the probability the number of runs is 3. I find all outcomes where the number of runs is 3. Again, there are 6 in all, so the probability z equals 3 is 6 out of 16. So at the end of the day, I have 3 probability distributions. I have 3 random variables associated with this experiment, and I've written out 3 tables which give me a representation of the 3 probability distributions, one for each. I can also represent the probability distribution for a discrete random variable with finitely many possible values using a graph. And we've actually done this in the previous section for our probability distribution for experiment A and experiment AP, which actually had infinitely many possible values for the variable, but nevertheless it was discrete. So recall how I do this. I form a category which contains each value, well, a category for each value of the random variable, and I'm going to center it at that possible value of the random variable. And that category, or that interval, should not contain any other possible values of the random variable. And we make each category of equal width so that our final graphical representation adheres to the area principle. And above each category, we draw a bar whose height is equal to the probability of the corresponding value. If the possible values of the random variables are integers, then it's easiest just to make each bar have a width of 1, or a base with width 1. And here's our example. If I flip a coin 4 times, let x denote the number of heads, then we have the possible values of x are 0, 1, 2, 3, and 4. And here we've drawn a bar centered at each of those possible values. And the width of the base of the bar is 1 in each case, so they don't overlap. And the height of each bar is the probability that each of those possible values of x occurs. How do we use this graphical representation? Well, the graphical representation contains all of the information we need about the probability distribution. So we can actually use it to calculate probabilities. The total area of the graph we draw, the bar graph we draw, should be 1 if the base of each of the rectangles equals 1. And we can calculate the probability of any particular set of outcomes by summing the area of the graph above those outcomes. So here, for example, we have the probability distribution for a random variable x, a discrete random variable, whose possible values are 1, 2, 3, 4, 5, and 6. And the area of each of those bars is equal to the probability that that value will occur. What is the probability that x is less than or equal to 5? Well, it's actually the sum of the areas of the rectangles above 1, 2, 3, 4, and 5, which are now the blue rectangles. And we can see that that's 0.1 plus 0.2 plus 0.2 plus 0.1 plus 0.2. It's 0.8. Another clever way to do this is to say, well, the total area of the distribution is 1, and so I can calculate the probability x is less than or equal to 5 as 1 minus the area of the red bar, which is 0.2. So that probability is 1 minus 0.2, which is 0.8.